things that you've heard about today and saw with your own eyes in terms of the demonstration, in terms of the impact of the project, both what works, but also to reinforce many of the things that the student presenters said today about the way in which our technology is being disseminating and having influence. Now, of course, it's always a good idea to define what you mean by impact, and a good definition, this is actually due to Satya at Carnegie Mellon. He defined impact for me as work so significant that others must build upon it for their own success. And that works as well for software, where other people use your software or incorporate your algorithms into the kinds of software and systems they build. And it works for theory, because they sort of build on the principles, theorems, and so on, the formal framework that you construct as well, in order to enable their own research. And this happens within our projects, because we're multiple faculty and a large number of students spanning systems disciplines and machine learning on this particular project, and you saw a lot of the sort of interactions across those disciplinary boundaries, which frankly are very rare to find in most university research projects, which are more along the lines of one, maybe two faculty members working in a very domain-specific research area. So we're going to talk about these things. Now, the RAD Lab impact, one thing as sort of a warning, a caveat before we start is it's really hard to know what the real impact of a project like this will be at its immediate end. One of our most significant projects from early in my career, the SPUR project, which was actually to build a multiprocessor list workstation. At the time, we thought things like stooping caches were a really big development of it, maybe some of the aspects of floating point that we did. It turns out that commercially, the major impact of that project was really the HDMI graphics or video input format that came out of some of the work of the students who worked on that particular project, building the clock distribution system and having a very clever silicon implementation of a tunable clock. Turned out to be the basis of digital video interface that we all use on our high-end TV sets at home and outputs from computers and stuff like that. And who would have known that really the technical gem that underlies all that was something that came up in that project. As Patterson said the other night, it wasn't even on our list of what we considered to be the actual contributions of the project. It's probably generated the most money and commercial opportunity from that project. So the way I'm going to go through this potential impacts is to work bottom up from the processing infrastructure all the way up to the applications, which is a little bit the opposite of kind of how we went through things today. We went the other way through much of the day. And also I want to talk towards the end of this about the collaborative processes that we have within the project and our educational contributions, which I think are a very significant piece of what we've done. And the sort of 4 Ps are a very important aspect of this. The people who you have been seeing on the stage all day, the prototypes that you've been seeing demonstrated, and the way in which they have been already disseminated and in some instances picked up by industry through open source distribution. Obviously the papers and so on are a more traditional kind of impact, but I want to highlight a specific paper, the Above the Clouds technical report, and the influence that it has. And then there's a lot of principles that underlie this that turn into the theses of the various students that have been working on the project that are, again, a very important, albeit traditional, way of talking about the impact of a project. So this is the RAD Lab Architecture. It's more or less the prototype system that you've seen today. There are some pieces on this that have not been demonstrated to you yet, or include certain componentry that sort of evolved over time and are not actually shown in the final demo. But this is what we use to try and understand the overall structure of the system and the different componentry within it. And I want to use this as kind of like my agenda slide, so you know you are here when I'm talking about different elements of the impact. So one of the things that I want to start with is to really talk about the underlying processing infrastructure that is below any of the software developments that we had. And the major elements of the kinds of work that we do in a collaborative project like this, which has a lot of interaction with industry, is we were going to work at data center scale, but we were not in a position of building our own million-node data center. So how are we going to do that at the beginning of the project? Well, one of the things that we tend to do that's kind of a competitive advantage for our projects is through our industrial interactions, we have early access to leading-edge technology from our industrial partners. And in the case of experimenting with data centers, our kind of angle on that was to work with Sun Microsystems and make use of the black box, which in our case actually is a seafoam green box behind Soda Hall. And in fact, a little interesting story about the free piece of hardware that we received, which is the Sun Black Box, cost $50,000 to actually haul it in, install it, bring power and cooling to it, build the enclosure, put the locks and security systems on it, and so on. So it wasn't really a donated free piece of equipment when you think of the operational cost for it. And that's the video loop that's running in the background, actually on the displays that are on the wall just on the other side of the back of the room. But our plan was to use the black box, which would give us a lot of computational ability, order 1,000 servers in that one physical kind of data center piece. And an element of our original proposal was to use the real data center building block, which was the black box, but also explore order 10,000 node processing using a technology called data center in a rack, which is still being developed as part of the dissertation of Zhangji Zhang. So if we take a look at that, we've actually made some progress on that and like to talk about it. The field programmable, the idea of the data center in a rack is the field programmable gate arrays. This actually is the prototype B3 system, which is constructed out of 4 of these very high-end field programmable gate arrays. That is the substrate upon which Zhangji's implementation of essentially, think of it as field programmable gate arrays that have multiple hardware threads that they can support. And so one piece of hardware can be time multiplexed to form the function of a processing node or a network switch using the same underlying substrate. And so in this system, we're able to put together, albeit at a significant elapsed time slowdown, in just one of these things, we're actually able to emulate 512 full SPARC processors with all of the necessary peripheral hardware like memory management units and so on in order to run the full Linux stack, software stack, all the way up through applications. We're able to do that on one of these, and each one of these pieces of hardware are able to support 512 servers and 16 32-port kind of switches in that environment that allow us to build a network interconnection amongst them. So one of those is a piece of a data center, and if you were to put 20 of these together, which is not an unreasonable thing to imagine in a university machine room, we would get up to that order 10,000 nodes. And the feedback that we got from talking to our sponsors like Google was 1,000 nodes is 100 nodes is not a good number for really understanding the scaling issues in data center applications. You got to be in the range of 1,000 to 10,000 to really see the scaling issues. And so our strategy for doing that was to use the data center black box as the order 1,000 nodes and to move up to the implementation of data center in a rack times 20 in order to get up to the order 10,000 nodes. We never really use this for our own applications and demos because the hardware is just now becoming available to us, but it has been used to study some of the phenomena that we saw as being problematic performance at a network level inside the data center, the TCP incast problem. And it was also used in collaboration with Chuck Thacker at Microsoft Research to investigate a new organization for data centers that he, as a hardware designer, came up. He was able to use this particular hardware structure as a way of investigating the hardware trade-offs in that new design concept that he had. So a way in which technology that we developed sits on top of the hardware that Chuck developed with the sort of way of personalizing it to turn it into a emulation, albeit with 1,000 times slowdown of a data center, including all the network elements within the data center, that in turn Chuck was able to use on top of that the ability to investigate a new entire structure for the data center. So the thing that's really cool about this, of course, is one of the things that often happens in university projects are you never want your research success to be gated by depending on someone else. That's usually people think of that as a mistake. Here is something where we depended on Microsoft to pursue our own research, which in turn Microsoft depended on our stuff working for them to make their progress. That is a fantastic example of impact. So moving on, the next thing we're going to talk about is really the monitoring infrastructure. And an important element of that early in the project was the work of Rodrigo and George on XTrace, a cross-layer tracing tool, which we used in the early part of the project. It's an idea that involves tagging the packets as they move through the network with protocol information and source and destination information and network element identifiers, so that you have a way of determining how far, what progress packets have made on their transport through the network. And by being able to reconstruct the information from these packets, you can build a tree that was shown in one of the talks earlier today that allow you to really understand how far the processing of those packets have gotten, both in terms of the protocol stack, sort of vertically, and then horizontally across the network. And this is actually has had some of its own impact. It's available through SourceForge, and there's a website describing XTrace. It was used to support the debugging and troubleshooting in a research project initially developed at Stanford and then transferred with the graduate student who became a faculty member, Mike Friedman at Princeton. Part of Rodrigo's dissertation discovered a whole slew of distributed system errors using XTrace in the Coral content distribution network, which turns out to be a very widely used open source content distribution network software. So very successful in that, and it actually has found its way into a tool set by a commercial company, and we believe, I could be corrected, that it provided some inspiration from some of the tracing tools that are part of the Cloudera software stack. We would not claim that they use our software. Ari mentioned Chukwa earlier today when we were talking about the sort of part of the demonstration which is collecting this data so as to be able to feed it into a visualization system. And as he mentioned at that time, it's a large-scale log collection system based on MapReduce processing. It uses Hadoop. It uses the Hadoop file system. And the thing I find really cool about this is Ari started that project as an intern, summer intern at Yahoo Research, working with some of the engineers there. It got turned into an Apache project. It has been, I think it's pretty cool that, sort of a first or second summer student working at Yahoo has been able to develop some software that is the basis under which today order 20 million subscribers are using Netflix. The underlying use of Amazon Web Services to support Netflix video streaming is collecting statistics about their servers and services and processing it using Chukwa. This came out actually at the NetApp University Day just like a week ago or so, which is pretty cool. And he also mentions CBS is using it, and we understand or have heard rumors that it is in use at Cisco as well for collecting monitoring information from deployed routers. So it is a kind of software widely available. There is something of a user community of developers around it, and it is in use in several large-scale, highly visible websites. So moving on again, let's talk about the SCADS layer and the Pickle language, and of course the scalable storage that is a very critical part of the demonstration that you've been seeing today. You know what it stands for: scale-independent structured storage for interactive applications. Pickle as a query language that works hard to meet your performance bounds in the way in which it processes queries, a very important idea. The sort of response time limitation to the query processing that gets done. The scalability of SCADS for an implementation of the distributed key value store. As demand increases, copies get made. As demand decreases, copies are retired. And you have seen that actually working during the demo. And really the impact on this one is too early to tell. I don't have a story about how this has migrated out to industry or that kind of thing, but it will be continuing to be a very critical piece of our next generation project, the AMP Lab, which is going to be much more data-oriented and data-focused than the RAD Lab was, which was more about managing cloud processing and services. So impact yet to come in terms of the storage elements of our system. Now, Matej gave a wonderful talk on the sort of operating system for the cluster built around the Hadoop processing environment and some of the extensions that have come on top of it. And just to hit some of the highlights from that, which he mentioned, but to come back to it, Mesos, which is kind of based on the experiences of working with Hadoop, adding new scheduling algorithms into Hadoop, the grad students working on the project came up with the idea of building a multi-level scheduler. How can the sort of scheduling framework, as they were investigating in Hadoop, can be kind of as a thin layer, provide a foundation upon which many different frameworks can run. And so this has, in part, because you'd like to be able to use the same collection of cluster resources to support MapReduce processing, as well as web services processing, as well as sort of general purpose high performance computing or that kind of thing. And so excellent motivation for that, and as Matej mentioned, it actually is what I think for university developed software, the fact that Mesos is currently running on a more than 100 cluster setup, 100 node cluster at Twitter, running operational code as part of the Twitter underlying infrastructure, is an incredible example of university software impact. And it is being tested at Facebook and is still kind of under evaluation there. So major really impact in terms of industrial practice. Of course, as Matej pointed out, Mesos underlies everything you've seen running today. So it really is functional, operational, and furthermore, the guys building the infrastructure and the guys building the storage level and the guys building and girls building the applications, all of these things are running on top of each other throughout the day in the demos that you've seen. The stuff actually works and is dependable enough for this demonstration. Now, as follow-ons, additional impact, we've had a lot of detailed interactions with Google about future scheduling ideas. Andy is currently on an internship working with Google people in Seattle to understand workloads, and we'll continue interactions with the people who are working on schedulers inside Google. We believe, Matej did not say this, but I'll say it, that we certainly have been tightly engaged with the folks who are the critical leaders of development of Hadoop, currently housed at Yahoo. They have come to our retreats. They have seen our ideas on Mesos for at least a year and a half, if not longer already. So it's not too surprising that, at least as it's come out as a sort of news report or blog entry, that the ideas for Hadoop Next Generation clearly bear a stamp of having been influenced by the ideas inside Mesos. There has been other work. Ganesh has done work with researchers at Microsoft on understanding outliers in their framework for a kind of processing that is similar to MapReduce, Dryad, and to investigate scheduling algorithms and response mechanisms to deal with outliers, processor nodes that are going very slow. So further interaction with our sponsors, and it does provide, in the future, it will continue to provide infrastructure foundation for everything we do in the AMP lab. Now, coming back to some of the cluster computing abstractions, as Matej pointed out, several of the ideas have made their way into Hadoop, which is really widely used now. There are a lot of websites that are currently, or web properties that are using Hadoop for its log processing or any sort of background analytical type jobs. And the late scheduler, that was some very early work done in the group, is now part of Hadoop version 0.20. You heard about Spark, better support for iterative applications. Again, an example of a close collaboration. The machine learning people, Justin, depending upon the underlying scheduling environment being able to work, or the execution framework of Spark, depending on his success for Matej delivering on a working framework for iterative analysis like Spark. We are breaking that never depend on anyone else in doing your own research. We break that sort of axiom all the time, which is a good thing. Gunho has done work on hybrid data centers, and other students in the group on energy awareness in data center environment. Gunho, in his qual exam, came up with the idea of progress share, which continues to be a point of interaction with Intel researchers on how to sort of organize data centers where the nodes are of many different types, and what does it mean to have fair sharing of an environment where you have the underlying hardware resource is quite heterogeneous in the nature of the resources that are available on the processing nodes. So again, great interaction between machine learning and systems researchers in terms of Spark, interactions with the general open source community and with specific sponsors, and a way in which publications also lead to continuing influence through also developing open source software which is widely distributed. Okay, moving up now in the direction of application support and the director. So key thing here, of course, is one of the main bets that we made early on in RAD Lab was that we were going to make statistical machine learning a first-class citizen of system architecture, and we were going to make use of it, and we have shown you examples of how it was used for debugging, monitoring. We have also used it in power management, configuring of nodes, predicting performance. You have seen some examples of that already. Certainly Waze work on console log mining, a very interesting and highly visible application of machine learning and system technologies to try and understand the source of failures inside operational cluster environments. There is a sort of fame factor associated with being able to present this work by invitation at one of the leading machine learning conferences as a way of motivating, inspiring machine learning researchers to better understand what the system opportunities might be for the use of machine learning technologies and systems. And didn't get a chance to check with Wei about this, but I think certainly the initial console log mining results were based on a collaboration with Google to get access to real-world logs, and it may even be currently having some influence on Google's internal processes for examining log information for errors and so on. KCCA and the use of it to understand sort of performance models and the best way of configuring the underlying cluster. KCCA is a Michael Jordan invention with his graduate students, a very particular way of building sort of graphical algorithms for machine learning. It really is based on execution traces with these techniques to understand how you can make predictive performance models in a way quite different than the traditional performance measurement kinds of techniques. And we have used it to understand utilization and latency trade-offs in the way you configure the underlying system to support a particular application set and performance objectives for those applications. And we've also exploited these techniques in figuring out whether a particular configuration will meet the service level objectives at compile time instead of having to run it at execution time, and have even extended it into environments like security, intrusion detection. Can you understand the nature of intrusions even in an environment where you have a smart adversary who knows you're watching and monitoring and is trying to trick your machine learning algorithms into the wrong corner so that they can come and sneak around you to break into the system? So this represents a lot of the PhD kind of level of research that have gone on. Some of the work has been highly recognized in particular research communities. Final piece, of course, has been an underlying major element of today's demonstration. Peter's dissertation, the work that he's done with Beth on the auto-scaling of the underlying resources to support our scalable web applications based on the performance models, based on the ability to predict and to identify and predict spikes in workloads and to appropriately respond to that by the marshaling of resources to meet those spikes, as well as they are spikes, so they go away. So also retiring the resources that you needed. And so that is really embedded in the director prototype, which you saw in today's demo. And a recent presentation on this to the sort of file and storage research communities, one of their key conferences, was extremely well received, and we expect that to continue to have be further developed and continue to be an important element of the future AMP Lab. Now, kind of switching away from just talking about the RAD Lab architecture, but now general collaborative processes, technologies, and so on, one of the things I think we can lay claim to is very early adopters of third-party cloud computing capabilities. We learned about Amazon Web Services beyond S3, EC2, in the time frame of the end of 2007. We got very significant feedback from our research sponsors about well, you guys really have to build this system at scale in the time frame of our January 2008 retreat. And by June 2008, we had lots and lots of results around the initial investigations of Hadoop at scale and so on, based on experimentation we were able to do with Amazon Web Services and EC2, doing experiments of our new scheduling algorithms using 1,000 nodes. And as I think Michael mentioned earlier today, yes, you asked for 1,000 nodes. You actually at that time got a phone call from someone at Amazon. Do you really want 1,000 nodes? We could buy 1,000. Are you willing to buy 1,000 nodes? You know, kind of that sort of thing. We really were breaking their system at the time. So very early adopters of Amazon Web Services, as certainly one of the first university research groups to do that. The scalability feedback that was realized by summer. A lot of the things that you have seen running throughout today, the MapReduce benchmarks, the RAIN workload generator, all driven by really this desire to work at scale. And the way that we do it, we sort of prototype these things on the processors that are inside the black box, but we really test them out against Amazon Web Services, and on 1,000 nodes is now, you know, sort of the standard number of nodes in the kind of systems that we test, not an upper limit on that kind of thing. So I believe that we were probably, at least in the systems research community, the first to perform 1,000-node cluster experiments on EC2, because we were doing it in spring of 2008. But it's quite possible that we were amongst the largest users, if not the largest users, at least in terms of number of instances, if not in total CPU hours in the time frame of early 2008.
I can tell you that we were, in fact, the largest non-commercial user.
Okay, and it's getting the right set of adjectives right. I try to do that. You see, I kind of...
Yeah,
yeah. I think I kind of got it, more or less. Okay, so our shared collaborative research space, I think many of you have seen the space that we have for the RAD Lab over on the 4th floor of Soda Hall, the southern part of the building. One very significant dimension of this, by far probably the most important one, is Dave and I have been at this game. The two of us, you know, in sort of sum, have been professors for, you know, pushing 65 years now. So we've seen a lot of these kinds of projects and many, many generations of graduate students over that period of time. I have to say that the group that you have seen demonstrating technologies today is by far the fastest bootstrap to important ground-shaking kind of research. The sort of work that first-year, second-year students were doing in our lab is the sort of things we would have expected third- and fourth-year students to be doing. So there was something about the space, the collaboration, the intermixing of senior students with more junior students that got our students into research at light speed compared to the more traditional way of segregating students by their year and putting them into dark holds of the building and so on. And there are many things that, you know, we haven't done the social, we see the results, we don't know all of the, we understand there are correlations, but we don't really fully understand all of the causality dimensions of it. But certainly the fact that the faculty, postdocs, and students are in a common laboratory space has led to, I really think the RAD Lab layout is optimized for graduate students. It may not be optimized for faculty, but it's definitely optimized for graduate students. We are accessible, it's great for interaction. It's great for us to kind of drive the students forward because we know when they're in the lab, all of those kinds of things. If you haven't seen it, I think most of you probably have, it is really as a, you know, building on technology, I think we were greatly influenced by the structure of how Google organizes its corporate environment. So open plan workspaces, separate meeting rooms with conference phones, very rich display environment in those conference rooms, floor-to-ceiling whiteboards, low partitions, friends from HP Labs. This is so that you can kind of stand up and see where everyone is in the space. And if you have that kind of, you know, and also to allow light and air to circulate in these inner recesses of the lab space. But if you do that, you have to have a quiet kind of work environment if you're going to do that sort of thing. And that is part of the social rules that are supposed to be enforced there. Dave is a big fan of reading all these books on how to organize space, and there actually is a planned flow with a single entrance So everyone more or less has to walk by each other, and a lot of stuff is centered around the coffee area and the kitchen area. And it's influenced other spaces at Berkeley, and many other university groups have come through to take a look at it, and we think we've at least had some influence on them. We actually had to go back, and this is something that evolves. We've reconfigured the space for more meeting rooms. There's never enough meeting rooms, it seems. And there were some needs for private offices for the staff. And it's such an interesting environment that it has had the function of attracting new faculty to the space. David Culler for the Locale project and Mike Franklin for the AMP Lab. But we're planning to continue to call it the RAD Lab because, after all, it is the Randy and Dave Lab. The retreat model, I think just about everyone here has participated in a retreat. And so you know that's a way in which the project team comes together with our collaborators and sponsors, really so you get to know the people and try and hire them, to find out where we are and to see our work in progress and obviously become aware of the prototype technologies that we're developing. We also get a lot from those retreats. We get the early access to technology, like the black box, maybe like some new things like Hadoop, finding out more about Hadoop, inviting Owen and all those guys from Yahoo to come to our retreats because we were starting to work with them. Also promising directions and feedback. You better work on scaling are really very important dimensions of that, and the 2 meetings per year, typically in January and then again at the early part of the summer. And we continue that with the AMP Lab and the Locale and just everything we do. Publications, you can find them on the web. They have appeared in prestigious venues, many of the leading system conferences and machine learning conferences. And I think we've been highly visible in a lot of the leading edge workshops that are sort of geared towards this emerging new technologies like cloud computing, the Hot Cloud Workshop, Power and Systems, Symposium on Cloud Computing. There are zillions of systems and machine learning workshop. All of these are examples of very topical kind of meetings where we have tried to assist in the organization and publishing papers and so on. As these topics become more mainstream in the conventional conferences and so on, these workshops are a way of that transition process. Now, the Above the Clouds, so there's lots of papers you can go look at and see how many citations and so on they have. I haven't added them all up, but I want to talk about one, which is the Above the Clouds Tech Report, which is one of these. This is now turned into actually a verb to have a Berkeley view. I was just at a College of Engineering meeting where they were talking, we need the Berkeley view of energy. We need the Berkeley view of sustainability. We need the Berkeley view of security. So now this idea of a group of faculty and students coming together, writing a vision type paper, white paper, which talks about the current state of the art, the technology trends which are driving it forward, using Dave's sort of terminology of pitfalls and fallacies or opportunities and restrictions. You know, capturing all of that stuff really helps galvanize a research field because now there's a common terminology, there's a set of basically the equivalent of the Hilbert problems in that field that help people kind of understand what it is they have to go after. And I think one of the things when you kind of do a search for images related to the tech report, you get that one, of course. But the one that got a large number of Google hits was this one, the top 10 obstacles and opportunities for adoption and growth of cloud computing. A lot of people use this. We received ourselves about 5 million mail messages of, thank you very much for your tech report and your identification of performance unpredictability as one of the major obstacles. Our product solves that problem for you. And of course, if the interest is in the academic figure of merit, I know it's sort of off on the side here, it'll be a little hard to see, but according to Google Scholar, we now have for a paper that was published in February of 2009, so it's 2 years old. It has over 800 citations, both attributed to the, in sum, attributed to the CACM version of it as well as the tech report. So, and of course the tech report has probably 80% of those citations. So interesting, a tech report hasn't appeared in any conference or any journal, has 600 citations or something like that by itself. It is indicative of the right kind of thing written can have a really tremendous impact, really influence other people. Well, of course, in these projects, the people are really important, and the educational goals, the human capital and PhDs, A large number of people have been associated with the project and finished with the project in kind of a pipeline fashion. Some of them have gone to academia. Many of them have gone to companies which are sponsors. Some have gone to startup companies. So you get a sense of where all of the people have gone, the PhD students. And of course, there are many who are sitting in this room who in the next 12 months, 18 months, 24 months will be graduating and in a way will count towards AMP Lab, but also will count them again here. Undergraduate. So I think one thing that is unique in my experience of these kinds of projects is the very high degree of undergraduates that have been involved in this, and kudos to Armando for really wrangling. He's the undergraduate wrangler in some sense. So undergraduates have worked on applications and on the infrastructure that you've seen demonstrated today. Quite a few of them have graduated and are working at a variety of startup and mainstream companies. Some have gone to graduate school. There's only actually a relatively small subset of them that are here supporting the demo that you saw today. And we should also mention Will Sobel, who was one of our, we hired him kind of as a consultant staff member to really help bootstrap our endeavors in using some of the agile development technologies that form the basis for the scalable web applications. Oops, went too far. So let's talk about some of those curriculum innovations. Well, a lot of the undergraduate courses were new and revised. Armando introduced an experimental software as a service class for the undergraduates, and the best ones were picked to work on as researchers on the project, where he introduced Ruby on Rails programming into that environment. One of the early goals of the project was to sort of design our own programming language to help in the rapid development of these scalable applications. And along the way, Ruby on Rails came to our attention, and we change our minds. I think that's an attribute of our projects. When a technology comes along that solves the problem, let's jump on it rather than try and reinvent it. So Ruby on Rails is an example of that. The Amazon Web Services is another example of using great technology that's out there rather than trying to reinvent it. Armando has now transitioned this set of courses and curriculum into our standard undergraduate software engineering class, really focusing on agile development. One of my contemporaries, a friend from graduate school, who has worked as a professional starter of software companies for the last 35 years, he actually came across Armando's lectures and was waxing wonderful about how great the material is and how much fun it is to watch these lectures, which are available, I guess, through Berkeley University on YouTube. So a lot of this stuff is getting out there in ways you couldn't even track that well in terms of influencing programmers and programming process out in the greater world. Dave and Dave disappeared for an hour and a half this afternoon to teach our course on great ideas in computer architecture. So these are third semester computer science major course in the programming sequence. Mostly sophomores, some freshmen, are writing non-trivial applications using EC2 as their first project in their third semester programming class, and the vast majority of students got it working. Like 95% of them, 96% of them, something like that. So we are introducing parallelism and these kinds of ideas very early in the curriculum and sort of trying to reinvent computer science at Berkeley from the bottom up, from the introductory courses forward. And very important set of concepts that are in there. The graduate special, a whole slew of graduate special topics courses, Internet Data Center Architecture, Cloud Computing, Software as a Service. Mike Jordan and his postdocs have done yeoman service in offering, towards the beginning of the project, kind of every new academic year, a practical machine learning boot camp, where we could bring the system students up to speed on the latest machine learning ideas so that they can try and embed them inside their systems. And the student impacts, well, clearly our students have done pretty well in a tight hiring environment because they are steeped in the latest industry-relevant tools and methods for rapid development. So that's been really great for them. Some of that material is now in discussion with Google to distribute to their Code University because they see the value of getting these kinds of new age curriculum materials out to a wider community than just students at Berkeley. And Amazon also uses our projects and laboratories related to their services as part of their sort of collection of courseware to sort of incentivize other instructors to start doing the same thing. And thanks very much to Amazon for the fantastic support they've given for academic course instructional use of their technology. It's really been great. So coming towards the end here, the RAD Lab impacts, as I said, these are potential impacts. The real question will be when we have a 10-year reunion, as we do for these projects. Dave will be ancient, Randy will be 65. We'll come back and we'll see just what the real kind of lasting innovations from the project have been. Here are the things I've talked through. I won't, in the interest of time, mention them again, but each one of these things has been part of my presentation. And remember, in the end of the day, RAD Lab is people, just like Soylent Green. So this was our latest winter retreat. The summer retreat before that, you see some of your pictures in there, I'm sure. The winter retreat before that, and the summer retreat before that. And the winter retreat before that. I think with that is probably the end of the talk. Just as the last point is, when we started this project, our motivation was how hard it was to get large-scale funding from the government to do the kind of research we wanted to do. We understood that we needed to do it with industrial support. Dave and I went to a meeting of all the industrial laboratory directors in Silicon Valley. It's called the BARD Group, Bay Area Research Directors. And Alan Eustace was there. And we basically, at that meeting, lamented about the state of government financing for large-scale computing systems research, made a pitch to him, convinced him, Google signed on. With Google in hand, we were able to use our wonderful long-term, multi-decade relationships with Sun Microsystems to get them involved. Google and Sun, we were able to convince Microsoft to be our really core large-scale funders, and then a wonderful collection of companies with unique technologies that we could work with, that were supported financially and in terms of technological advantage, and so on, to make our project a success. Really, at the end of the day, we have to thank you because you guys paid for all the stuff we've talked about today, all the training of students, all the technology development was made possible by your sponsorship and your patronage throughout this project. And with that, I think I'm done, and we'll take some questions. Amar.
It's great, excellent. I mean, presentation, see all of the accomplishments. One question, though, if you would have done something differently, like what's the learning lesson from RAD Lab that you would like to feed into AMP Lab going forward, if any?
That's a really good question. I also will need some help from the other faculty. I think one of the things that is not necessarily a lesson learned, but something that we already knew is we're working in an area which is really kind of in the wave front, slightly ahead of industry. And so it's very important to be able to tackle and to redirect yourself to stay ahead and not simply duplicate what industry is doing. And that's it's not something we would do differently. It's something that we have to be even more aware of as we now move into this data-intensive computing arena. There are a lot of companies, a lot of technology that's going to be developed. We have to be always cognizant of what our value added is, and when appropriate, give up on something and just build on what industry is developing, as we did with things like Ruby on Rails and Amazon Web Services, EC2. So I think we want to be out in the sort of use of machine learning in our system architecture and so on. That is well ahead of where industry is today. The kind of monitoring infrastructure and so on, we contributed to open source, companies jumped on it. That's not what Ari's dissertation is going to be. He moved on from that. So, there's lots of examples of we can do great stuff, but you have to keep having your eyes ahead so that you continue to lead the community, and I think it'll be even a bigger challenge for us in AMP Lab and dealing with the data deluge just because of all the interest in that, but I'm confident that we have the ability to do that. But that's a good, thoughtful question.
Yeah, I think.
Yeah, other faculty, if you have thoughts.
I mean, I don't know what Bill's going to say, but a lot of this worked, right? 5 years ago we said we do this. I think one of our anxieties, we'd never done a primarily or almost exclusively industrial funded project, and there was a lot of concern how that was going to impact the research agenda. Would we continue to be able to set our agenda, listen to feedback, and do what we want? What about, was there going to be patents? Was there going to be publication problems? There was a lot of worry. And when we announced, when we announced in December 15th in 2005, there were, the New York Times and lots of people covered it because, Google and Microsoft cooperating was kind of the news angle. And I got sarcastic email from faculty at like UC San Francisco. When does a colleague at another campus ever contact you ever? That's probably my third contact from another campus. And basically it was, well, good luck with all those companies, you soul-selling bastard, Yeah, because pharmaceutical is pure and above all that. But so there was I think there was concern, are we setting our research, I think till this day, right? Are we saying this is an exciting problem?
Tools of our corporate masters.
Yeah, are we saying this is an exciting agenda and then find companies who share that vision and support us, or is it are we, tell us what to do, right? So I think that worked out really well. The space was amazing. The space was an amazing, who would have thought that how we organize the space would accelerate the rate of graduate students doing research. Who would have, if space, it even helped us with recruiting. Who would have thought that space would help with recruiting? The other thing we tried, that I think it was Armando's idea, which was, why don't we do joint supervision? I don't think we mentioned that. Why don't we, as long as we're doing all these things different, new space, new funding, why don't we try have as the norm multiple faculty supervising students? I think it was partly the space had something to do with that. So I think all students, Armando and I co-supervise all the students. I felt like listening to Armando's advice, boy, these students are getting really great advice, and then when I was traveling, there's somebody there. So I thought that worked really well. And there's some people in here who I'm not sure how many advisors they have. I see meetings with unnamed people, and there's at least 5 faculty. There's this student, not named, and at least 5 faculty, and I'm a little unclear who their advisor is. So they fully took advantage of the open space and maybe lack of coordination between the faculty about who was their advisor. So, well, I'm sure this is like the George Bush question, right? What did you do wrong? I think there were things we were optimistic, like the data center in the box. Zhangji's still working on it, That was pretty optimistic. We thought we were going to get that there would be Sun would give us a processor, we'd drop it down in the FPGA, we'd put 1,000 of them together, and 3 months from now we'd have data center in a box. It was a lot harder than that. But Zhangji, to his credit, he's not giving up. He was going to do data center box. I asked him, you want to do something else, multi-core? No, we're doing data center in a box. So he's going to keep going ahead, and I think if he gets it working, he'll be able to answer questions that nobody, not Google, not anybody, because he can do experiments at the 1,000 process scale, but that's still... the fact that we're imitating this a lot. The one thing that we did in the PAR lab that I thought worked really well was closer ties with application people. We didn't do that here. In the PAR lab, there are people there. The AMP lab, we're going to do that. I thought if we'd had... our applications was the undergraduate students, right? We didn't have some kind of expert on campus on something that working. That was probably, most of our projects haven't done that, and I think that's a good thing to do. Other faculty want to? Yes.
So I'll say a couple of things, and it's not in the category of things we did wrong, but things that maybe is reinforcement that it's worth doing them again. One of them has to do with knowing when to take a chance on a student idea you don't really trust. And I'll just come out and say, when Wei started working on the log analysis stuff, Dave and I were frankly skeptical. It sounded like such a blue sky thing, right? Could you ever get anywhere with this? And it's yeah, exactly. And it turned into an SOSP paper, right? In a year when SOSP had like a 9% accept rate or something ridiculous like that. It was a paper in SOSP. It was invited to a machine learning conference. It's been remarkably successful. Google is now developing it further. So the right thing to do on that was just to say, okay, let's see where it goes. So that that was lesson for me. The other one, I think, especially in the light of the last couple of 3 months, watching everybody put the integration together. There's a standard criticism in all systems research projects that if you're spending time doing integration engineering work, you're not doing research. And I frankly just think that's not true. I think getting all this stuff to work together is way different than proving that your little piece worked. This is unit testing versus integration testing, and you learn a lot of things trying to actually get a full stack to work for all the pain that it is, and it's a skill that is important, whether you go into academia and do research or whether you're going to do actual products that are going to ship. I think it's an important part of the research experience, and I stand by our guns that the last 3 months, a lot of time was spent doing this, and that was time that was really well spent. And I think Michael did a great job pulling it together, and everybody who put in the extra hack nights and the, working over the long weekend to do another app so that we could actually concretely demonstrate the mission statement, that was great. I think 10 years from now, they'll look back and realize that it was good stuff. So we'll keep doing that again, and people who say it's not research or it's not moving the research forward, sorry, I think you're just wrong.
Can I ask you about that? Like, what do you think you've learned in the past 3 months?
Well, Michael's probably in a better position to answer that. If he wants to. He doesn't have to. He could answer it during the reception after beer. Let's do that.
Yeah, and it's actually it's time to.
Yeah, we need to get
on to Bill.
We'll use this. Well, I'm going to call people on stage.